Hi, so this is a quick video demo of the project I made to find the shortest path between towns, where we have pretty much three main classes, which I'll run through before we do the video demo. We have the graph class, which is like the big piece of the map, right? The second class would be the towns that belong within this graph or this map, and they're the towns. And then the third class would be the roads that connect the towns. So we have like a map with towns and roads that connect them. So our graph class uses a dictionary linking strings for town names to town objects and gives us the ability to do things like add towns to the map, add roads connecting the towns, checking if there are roads connecting two different towns, uh, all sorts of getters and setters and checkers for for finding the shortest path between towns. And I made this like maybe over a year ago, so I'm not super like, it's an old project, but yeah. Um, so about the town class, oh, I really like the way the town class is done when I look back at it. It has a name. It has an adjacency list, meaning all the roads that are adjacent or touching this town. And what we can do is we can iterate through that list to find what towns are connected to this town. And that's I mean, then when we're going through that, we can look at the weights or the distances of these roads, and we use that information with Dijkstra's algorithm uh, to find the shortest path between towns. So there's some fields here that we use that are here for using Dijkstra's algorithm, like the predecessor when we're traversing and trying to find the shortest path. Sometimes we need to store the the town that we came from to reach this current town while we're looking for the shortest path. It's just a thing. And yeah, that's the best I can say that. So yeah, if we can continue from there, then yeah, there's the current cost. I guess that would be total distance so far on the way on the path to our destination. And again, I'm running out of steam here, but let's just get through this. And then finally, I see here I have a dictionary. Um, okay, so we have a stack. When we find the shortest path, we'll store it in I guess a string. I don't know. We map a name. Yeah, I guess our destination. We'll map that to a stack, which will be a stack of the names. I see string here, so the names of all the towns that led the shortest path. So if that was easy to follow, I'll just wrap it up by roads will have a source and a destination, a source town, a destination town, a distance between them, and a name. So again, we have a map with towns and roads. Towns will have adjacency lists. Roads have weights, and we traverse these lists, and we store backtracking data to determine the shortest path between towns. So I'm glad I could get that out. Here, let's run the project. I like this one. I think it's like a mini Google Earth. And yeah, we can read from a file too. So um, that's neat. Let's go shortest path. Let's go MD towns. This is nice. I want to display the towns and the roads. This is really neat, right? Like these are the towns I recognize in Maryland, and these are a bunch of the roads. And so, like I said, each of these roads has a source and a destination. You can add more roads connecting towns and add their distances, and then you can find a connection from let's go from Gaithersburg to Rockville or Potomac. That sounds fun. And there it is. It'll tell us that the shortest path to Potomac would be to take this road to this town, and it gives us this distance. And yeah, so I think this is a really cool project. I'm actually probably going to expand on this and maybe make a web app or something, but add more visualization, and there's a lot of complexity that could be added to this sort of project, especially so. But yeah, before we dive into that, I'll just wrap this up and hope you enjoyed the video demonstration.